Welcome everybody, you're watching Mr. Fugu Data Science. I put together a few common distributions that I thought were useful with their PDF functions, a brief explanation of each, and a relevant plot to try to understand what's going on. Thanks to the recent subscribers and viewers, I greatly appreciate it. Let's get started. Here's what you need for the imports if you want to follow along. Otherwise, go to the link in the description and grab the code from my GitHub. We're going to start with the binomial distribution. And remember, each one of these will be for the PDF only. So remember a few things. It's a discrete probability function dealing with independent trials where each trial has an outcome of true or false, success or failure. All right, here's the mean and the standard deviation. I'm not going to break this down today. All right, if you want that, let me know and I could do separate videos for each one of these functions. So here's the code for the plotting. I'll let you pause this if you want to follow along with that or get some ideas of how this is put together. But let me explain something. Here's our binomial distribution with n equals 3 and a 50% for a probability or 0.5. All right, looks pretty typical of a normal distribution. Let's see what happens when we start varying the number of n. Keeping with the 0.5 for the probability, we notice something. As n increases, and look more like a normal distribution, okay? Which would mean that our standard deviation and our mean will change. Now, the Poisson distribution is interesting. It's a discrete distribution dealing with independent events with some expected number of events and some time interval lambda, okay? Here's what we're dealing with for the mean and the standard deviation. Now, you could use this in a few applications such as these if you want to read that, but let's get into what the plot looks like to get a general idea. So we can see that if we're dealing with lambda, that is actually our mean. For 1,000 samples with our Poisson distribution, we will notice that it looks somewhat like a normal distribution and skewed, okay? You'll notice this skewing. Now, what happens if we start playing with this? We'll notice that there's a trend with our lambda. As you increase your mu, you'll notice that this starts becoming a normal distribution with a tail. So as we increase our mean, starting with 1 and going down to 10, our sample will end up looking more like a normal distribution. That's the takeaway from this, okay? Now what is this Weibull distribution that we have here? It's continuous. It's used for time to failure events, given that you've survived thus far. The first thing that you should notice here is that at the beginning, you should always expect some failures. This stuff is going to seem pretty, like common sense if you think about it. You're going to have some constant amount of failures, and as you get older in life or more time goes on, you have more chance of a failure. So if you think about this in terms of your life, it's pretty relevant, okay? And you could relate this to your hazard function. I'm not going into that today, but you could look at what's going on with that because it's very relevant in the real world. Here's some of the use cases that we have for this if you're interested. Now, you have two parameters to think about. Your shape, which is your alpha, and your scaling, which is your beta. And then you just have some time for your quantity to fail, right? Is what you're interested in. Now, here's three particular scenarios. If you have alpha equal to 1, then you have a constant rate of failure. If it's greater than 1, the rate of failure is going to increase over time, and then the opposite if it's negative. And that would mean that you have like defective items. Now, here's the mean and the standard deviation if you care. And you could pause this if you're interested in plotting this out or seeing what was done here. So the first thing, varying the scaling here while retaining the same constant shape. And you notice the same thing that we're having in the other ones. You have this lowering, which would look like the mean is changing and it's becoming more broader and looking somewhat normal with a skew, okay? The next thing we'll look at is changing the shape. So here's the code for that. Now, when you're changing the shape, you'll notice that as you increase the shape, you're going to also increase the proportion of failures that you have. And what's going on here? It looks like it's becoming more normal, and this tail that you have on the right, where my cursor is, decreases immensely. So it looks like it's becoming somewhat normal. Now let's look at some very specific cases. For instance, if we were looking at the values of the shape between 3 and 4, we'll notice that it's becoming more like a normal distribution, but in this case, you're going to be more prone for failures. It's becoming more normal, but you'll notice that it's becoming more prone to failures at the end of its life. So take that into consideration. The next thing that we're going to look at is, let's say the shape was 2. So you see this skewed data going to the right, and you have to understand that the interpretation is saying that you have a sharp increase in the number of failures, and then over time it decreases. All right. Now, what if this failure is less than 1? Between 0 and 1, what happens? Well, you have this, the smallest number here, which would be 0.1. You have this extremely high drop off, and it looks like you're dealing with an exponential function. Then you increase this to 0.5, and it's not as steep, but you still have this drop off. Then you get to 1, and it's looking like it's, moderately sloped. All right, that's something to denote. And this would suggest that you have a high rate of failures in the beginning. Okay, now we're going to deal with the gamma distribution. You have continuous data. You have an alpha, which is your shape, and your beta, which is your rate parameter. And let's look at some of the uses, okay? We're going to deal with this one right here since it's an alternative and it's more readily used. There's some use cases that you could think of, and here's the mean and variance for these. Let's get into the graph to figure out what's going on. Here's the code for that, if you're curious. You notice this right here, this looks like an exponential function once again, okay? The takeaway from this, if you're increasing your mu, or for us, that would be k for the function above if you pause the code, as it increases, you have a flattening out. If, in the case of this exponential, alpha equals beta, which k equals mu at 1, that's when you end up getting this situation here. So if both of them equal 1. Then when you start raising this, let's make this a little smaller. Let's notice something. Here's when they both equal 1, 2 and 1, 2 and 2, 3 and 3, and 5 and 5, okay? So let's go back in here real quick and notice we'll have this really sharp peak, okay, when this mu is a larger value than our actual scaling, okay? Then we'll notice that as we increase that value, we'll have a lowering or flattening of this, and then as we increase the scaling, we'll end up having a more broader looking graph. If I increased the mu value, this would start increasing, okay? Now we have the F distribution, which is continuous. There's 2 types of degrees of freedom that are used in this function, and it's not symmetric about the mean, okay? Some common uses would be checking for the difference between 2 variances, or using it for ANOVA, or some type of inference, okay? And you have to define these as positive values as well. Let's look at some tips real quick. So if you have a large variance, put it in the numerator so you can have a right tail or a skewing to the right. If you're using 2 tails, then you need to divide by 2. The standard deviation will need to be squared to get variance, and you have to watch out for type 2 error, okay? So if your degrees of freedom aren't given, then use a critical value from a table, all right? Here's the mean and the variance for this. So let's scroll down a little bit. Here's the plotting that was done with this. Okay, and you'll see this highly skewed to the right data. That's fine. Just change some of the parameters and see what happens with this so we get an idea. As you increase the degrees of freedom for both, such as this, you see degrees of freedom 1, degrees of freedom 2. As soon as we start increasing both of these, you'll notice that an approximation of the normal distribution occurs. Okay, let's scroll down a little bit so you can see what this looks like. And here we go. At various degrees of freedom, as we increase the degrees of freedom, you'll notice that it becomes more like a normal distribution, and this tail, as usual, you'll see that it decreases the area under the curve here, and you still have this long bit. But this is what you need to pay attention to, and this right here. The next thing that we're interested in is the chi-square distribution. This is going to be something that's skewed to the right and continuous, just like our other skewed data. And here's a few use cases that you can have where you're looking for either the estimation of your confidence intervals, checking for independence, finding differences between observed and expected, or looking for a goodness of fit test. All right. Now, let's scroll down and look at this, okay? We're increasing the degrees of freedom, and you'll see that the mean decreases, you're becoming more normal, and it's also changing your standard deviation as well. But you'll still notice right over here, you still have this long right skewed tail, okay? Also, you'll notice something. Most books will tell you, hey, if you have 30 or more degrees of freedom, just consider it as a normal distribution. You'll see this noted in books and people in YouTube videos, so just be aware that that's just something that's commonplace that people say, okay? The student t-test is next, and this is continuous and used with hypothesis testing to estimate, for example, the mean of a distribution with some small sample size, or if you're looking for confidence intervals. The takeaway, as you increase the size, you get more closer to a normal distribution. And you have to remember that you have n minus 1 degrees of freedom, by the way. So scroll down and notice a couple things. First, right here, if you're looking to see if two populations are the same with respect to some variable, that's what's going on, okay? As usual, you increase the number of degrees of freedom. We approach a normal distribution. Okay, fine. You have to consider you're trying to look for data that doesn't have outliers and not a lot of skewness, okay? And usually you don't know your population. Instead, you're doing an estimation using your samples. So that's something to remember. I know it's elementary, but if you're new to this, these are just some hints and tips that are going to help you get through this, okay? So to scroll down and visually depict what's going on. As we increase the degrees of freedom, we get to this red one right here. It looks more normal. As always, pay attention to your confidence intervals, how those change, the standard deviation, and how your mean changes. Logistic regression, we're dealing with something that's continuous, great for categorical data, good for looking at binary classification, for instance. Let's see what's going on. If you're looking for something that's like chemical reactions or growth processes, this is also good. But here's what the plot looks like if you're curious for the code. This doesn't look very useful. It's just showing where confidence intervals are cut off for something that looks normal. Let's look at doing a comparison and change up our mean and standard deviations and see how this changes. So we're going to click on do our link that's based on Wikipedia, and let's scroll out just a little bit. You'll notice that here's our mean and here's our standard deviations that are changed. As usual, we're going to start with here. This is our furthest left with the smallest mean, the smallest standard deviation, and we're starting to increase going this way, okay? So here's where this dark blue is. We have a 5 for the mean, but a 2 for standard deviation. And then we'll end up having a 6 with a standard deviation of 2. And then we have a mean of 9, but we have a standard deviation of 3. The same mean, but a larger standard deviation, and that's where you see this flattening right here, okay? So that's a visual depiction of getting the PDF for the logistic distribution. Let's go to our last one, which is the Pareto, or Pareto, however it's pronounced, and it's a power probability distribution that is continuous. And you have your alpha, which is your shape, and your beta, which is scaling. Sounds usual. Here's some common use cases in the real world, okay? This is really good if you're looking at like stock prices dropping or anything like natural phenomenon, things like this, you know? So there's a lot of code for this one. Not sure if you want to pause that, but feel free. But let's just get an idea. As you increase your lambda and your k, in this instance, you can say that your alpha, which is going to be your slope, and this will be the k for this process, gets a steep drop off as you increase it, okay? So this is increasing and it gets this steep drop off, and your scaling is just moving it to the right. And we could think of this as most people have no money and very few people have a lot of money, like wealth distribution. You could think of that in this case. For instance, people who are making, you know, let's say about right here, $100,000 or more, the scaling would be different for your X and your Y, but it would still have this kind of drop off. And that's basically the gist of what's going on there. Well, it looks like it's a variation of the exponential function, okay? So, as always, I'd like to say please like, share, and subscribe. And if you subscribe, turn on that notification bell. Don't forget to hit me up on Instagram or Twitter, and I established Buy Me a Coffee because it takes a long time to make these videos. So please help me support this channel, and thank you for watching. Bye.